Hi everyone, welcome back to PW International Boards. Friends, in this class we are going to complete another chapter for our Physics Cambridge IGCSE exam, and this is going to be pressure. So in this class, first we are going to talk about the theoretical concepts, then we are going to solve some of the past year problems from this chapter. In this class we are going to basically talk about what do we really mean by pressure, what do we mean by liquid pressure and water supply system. After that we are going to talk about hydraulic machines, and the last portion is going to be expressions for liquid pressure, right? So first of all, let's first try to understand what do we really mean by pressure, right? So a pressure can be called as it is a force applied perpendicular to the surface of an object, right? So let's suppose we have got an object, and on that object we are applying a force, and we are saying that this force is actually perpendicular to the object, right? So this is actually very important. Now if you want to actually calculate what the pressure is going to be, in this case we are going to write that pressure will be written as the perpendicular force divided by area. So this is going to be the formula that we are going to be looking for. Now let's suppose that we have got a different scenario. Let's say that we have got a force which is acting something like this. This is a surface, it has got an area A, and now the force is not acting perpendicularly, but it is acting at an angle. Let's say something like this. And also let's suppose that we have got some this is vertical axis, and let's say this angle is with the horizontal axis, this angle is theta. So if this angle is basically theta, what we are going to say is that we are going to break down two components of this force. We are going to say that one of the component of this force is actually perpendicular to the surface, something like this, and one of the component is actually tangential to the surface, something like this. So again we are going to say that we will just talk about the force which is perpendicular to the surface. Only that force or that component of force is going to apply the pressure, or what we are going to call as pressure, right? So the formula for this one is going to be something like this, that is perpendicular force divided by area. And if you are going to talk about other things, the SI unit for force is Newton, the SI unit for area is meter square. So the SI unit for pressure is going to be Newton per meter square, which is also known as pascals, denoted by PA. So these are some of the SI units. Although for commenting about whether pressure is a scalar or vector quantity is slightly complicated than other physical quantities, but for when we are going to talk about the academics still high school, we are going to say that we are going to consider pressure as a scalar quantity. So this is actually very important, that we are going to consider pressure as a scalar quantity, right? After this we have defined what pressure is. Now let's move on and let's discuss some of the concepts related with pressure, or some of the examples. Now the first one is, they are saying a needle has a pointed end that has a very small surface area. Hence when a large force is exerted upon the needle with a hammer, the pressure on the needle increases, and it easily moves inside the wall. What we are trying to say is that if you want to actually increase the pressure or decrease the pressure, then the pressure is actually nothing but it is force divided by area. So if you are going to decrease the area, this will basically result in large amount of pressure, right? So that's what happens when we are talking about a needle or a nail. Shoulder bags always have broad straps rather than thin straps in order to minimize the pressure that would be exerted on the shoulders of the carrier due to the gravitational force acting upon the bag. So now over here the gravitational force is constant. I mean, if you have a bag, and the weight of that bag is, let's suppose it's 30 Newton, right? So for in that case, what we are going to say is that whatever the size of the strap is, whether it is broad or whether it is thin, the weight is going to remain constant. But what's going to change is that we are going to say that now for the broader strap, area will increase and pressure will decrease, right? So that's what we are saying in the second point. Third one, tools that are used for cutting and piercing always have sharp edges. So again, when you want to actually derive large amount of pressure, then you're going to talk about like sharp edges or small area as possible. Because as a person would apply a force on the tool, its sharp edges would exert more pressure due to less surface area, and the object would cut down easily. The two tires of a tractor are wider because it minimizes the pressure exerted by the tractor on the ground. As a result, it becomes easier to move the tractor on the muddy field. So it depends on what scenario you are talking about. So if you're discussing a skiing kind of a thing, like what usually people do skiing on a snow. So they have got ski board, and ski board has got greater area as compared to your normal feet. So in that case, again, we use this concept that if you have got large surface area, then pressure that is exerted by the force is going to be small. With that, you can also come across examples as of camel. How does camel move through sand without getting stuck, right? So that is also another example. After that, we are going to now talk about pressure exerted by liquids and gases. So when we are going to talk about pressure exerted by liquids or gases, let's suppose that we have got a solid body which is kept on a surface, something like this. So let's say this is the surface, and on this we have got a body, and let's say we have got a cuboidal body. And now let's suppose that we have got water inside of it. If it has got water inside of it, definitely the mass of the system will increase. And let's suppose that the weight of this system is acting something like this. This is let's say this is weight, that is W. This weight is being if I'll ask you that about which area this weight is actually being applied, so you're going to say this is being applied along this area. I'm going to mark it for you. So this is the area that we are talking about, right? Let's suppose the area of this, and since I took this as a cube, the area of this base is going to be a square. So in this case, if we are going to talk about pressure, we are going to say that pressure exerted by this cuboidal block is going to be weight divided by area, that is a square. So this is the case for solids, but when we are going to talk about liquids, liquids also exert pressure, and liquid exert pressures on the walls of the of the container. So these walls are going to experience pressure. All the 6 walls are going to actually experience pressure. The pressure that a liquid exerts on the bottom of the container is dependent upon the height of the liquid in the container. So we are going to now talk about it. We are going to say that let's suppose we have got a container, and the container is something like this. Let's say it's like a tube. So this will now depend on the height of the liquid. Why is that? The reason is quite simple. If we are going to talk about the pressure of different points, let's just consider pressure at different points. So let's consider this point to be A, let's consider this point to be B, and let's consider this point to be C. Now, if you're going to talk about point A, above point A, actually there is nothing, there is just atmosphere. And when we are talking about atmosphere, we are basically talking about gases, right? Atmosphere is nothing but gases. So gas has also got weight. So that weight is the force that we are talking about in this formula, that force upon area. So the force that the pressure that atmosphere applies on us on ground, that is known as atmospheric pressure. So if you are going to talk about point A, at point A there is just atmospheric pressure that's acting on it, and we usually write it as P naught, right? Now if you are going to talk about point B, so this is nothing but this was pressure at point A. If now I'm going to talk about pressure at point B, so I'm going to say we obviously have got atmospheric pressure, right? But along with atmospheric pressure, we have got some extra pressure because of the weight of this much amount of the fluid, So that amount of fluid or liquid is also applying force on the B particle, or at B, right? So we are going to say that now we are going to say P naught plus this access pressure is written as rho GH. So this thing is written as rho GH, where rho is the density of the fluid, G is the acceleration due to gravity, and H is the height that we are talking about. So let's say this is H1, so this is going to be H1. How we have come to this formula? We are going to derive it. After some time we will derive it, so you don't have to worry about, although derivations are not for your use because they are in exams they don't talk about these things. You are just going to be using these formulas. You will be needed to plug in the variables into this formula, but still for better clarity we'll look for that. When we are going to talk about point C, now for point C, we have got obviously atmospheric pressure, plus we have got pressure that is exerted by the entire this height of liquid. Let's say that height is H2. So I'll write it somewhere over here. Let's say this height is actually H2. Hopefully you can see this. This particular height is actually H2. So I'm going to write rho GH2. This is what I'm going to write, right? So that's how a liquid exerts pressure on a container. Gases also exerts pressure on a container. And when we talk about solid bodies, usually what happens, we talk about a certain force. So if you have got a body, it has got mass, then probably that force is going to be the weight of that body, right? Or it could be any external force like we have discussed in this example. Now moving on, again whenever you're going to talk about pressure is always the perpendicular force divided by area. So in all of these cases, when you talk about pressure acting on this wall, the forces that you are going to talk about will be in the perpendicular direction, right? Moving on, after this let's move on to the next concept. Now let's take an example. How you are going to figure it out, that what's the best way to figure out that pressure depends on the on what we can say on depth or on height. So what we are going to do is we are going to actually make 3 holes over here. So this is an experiment that you can actually do. We have got a cylinder of water. Water comes out of the holes, and now we are going to actually say that, let's say one of the hole is somewhere over here, the another hole is somewhere over here, and the third one is somewhere over here. This is the hole, and we are going to assume that we have got ground over here. Now what we are going to actually observe is that the liquid that is at the top of the liquid from the hole which is at the top of the cylinder will actually come something like this, and from this hole it would be probably something like this, and from the last one it would be something like this. And the reason for having this type of pattern is that the pressure at the bottommost point is going to be maximum. So the water from this particular hole is going to come out with greater velocity, and that's how the water is going to come. So it basically pressure depends on the directly depends on the depth. So as you're going to increase the depth, as you're going to go deep in water or any liquid, pressure is going to increase, right? Other than that, pressure also increases on acceleration due to gravity, and also depends on the density of the fluid. So rho, when we talk about rho is the density of the fluid, And when we are talking about basically fluid, we mean both the things, that is liquids and gases. Liquids and gases, right? Moving on, after this, we have got a similar example for gases. That's what I said, that whatever we are going to talk about liquids, same thing is going to apply in gases also. What's the difference? When we were talking about liquids, liquids are incompressible. So for liquids, their volume is going to remain constant. That means what we are basically trying to say is these are incompressible. Other than that, when we are going to talk about gases can be compressed, and the motion of the gaseous particles is something like this, that we call as Brownian motion, which is actually random motion. So these particles of the gases are actually colliding with the walls of the container, and that's how the pressure is being generated, right? So, gases also exert pressure on the walls of the container. The molecules of the gas of higher kinetic energy collide with the walls, applying larger force, and as a result these molecules apply pressure on the walls of the container. So same thing happens over here as well, right? So if the temperature is going to increase, we are going to say pressure will increase, because volume is constant. We are going to talk about this in gas laws again, so you don't have to worry about it, but just for now let's just discuss this thing too, right? Volume is constant, so if temperature increases, then they will because of thermal energy, they will actually collide more rapidly and with more energy, and that's how we are going to say that pressure is actually increased now. Moving on, we have already discussed what atmospheric pressure is. The layer of gases is present around the Earth's surface. The air present in the atmosphere exerts a pressure on the Earth, which is called as atmospheric pressure. The value of the atmospheric pressure, this you need to actually, I mean, it would be better if you'll remember it. It is 1.01 into 10 to the power 5 pascals. Now, this is actually very important, that this is at sea level. This is at sea level. So if you are going to actually go to higher to places which are at higher elevation, let me write it, at higher elevation, pressure decreases. The reason is that as you go up and up, the denser airs are all, or the denser gases are actually closer to the ground, right? So as you go up, let's suppose you are going for a trek or for a mountain trekking, you might have observed that you actually face lots of difficulty in breathing because oxygen is less. Next, there are various different things. A boiling point changes for liquid. Sometimes people suffer from nose bleeding. The problem is that our body is also maintaining a pressure that we usually call as, or we also call it as blood pressure, right? So our body is constantly maintaining a pressure, so that there is a no pressure difference between our body and the atmosphere. So when you go up, basically the surrounding atmosphere's pressure goes down, but still you have got like comparable, you have got higher blood pressure now, so that's why you have got those nose bleedings. For the similar reason, it is being advised that you must acclimatize for a few days before going through the base camp, right? So at higher elevation, pressure is going to decrease. That's what we have actually talked about, and when we are talking about fluids, right? Moving on, then we are going to talk about something that's called as hydraulic machine. And hydraulic machines are based on Pascal's law. Although Pascal's law is not in your course, but we can actually understand what do we really mean by Pascal's law. Pascal's law basically says that the pressure in a fluid transfers throughout transfers throughout the fluid. The only condition is that the fluid must be same throughout the fluid. And I'm going to give an example of this. Let's suppose that we have got a container, something like this. And we have got a small piston over here. And we have got a large piston over here. So this one has got area A2, this one has got area A1. And the main point is that it is being filled by with the same liquid, with the same fluid. So if you have got same fluid, then if you're going to apply a force on this piston, let's suppose you apply a force on this piston, and because of this force there is a pressure generated over here. So this pressure will be actually transmit throughout the fluid, and there will be no loss of what we can say, there will be no loss of pressure across the fluid, right? So same pressure you are going to actually experience at this point also. Well, the pressure is going to be similar to what this level is. So whatever this level is, so let's suppose pressure is P1 over here. So at this point also there is going to be pressure P1, right? So this will be used in different cases, like one of the cases hydraulic machine, in which what we actually do is a similar thing. See, we have got smaller area over here. So we are actually applying a very small force. So this is actually a small force. So a small force divided by even smaller area results in a significant pressure, that is P1. And because of Pascal's law, I'll say that this must be equals to P2 as well. This is what the Pascal's law says. And P2 is actually equals to F2 divided by A2. Now we know that, now we can see that A2 is actually quite large in front of A1. So to keep this ratio constant of F1 upon A1, what will happen is that this F2 force will actually increase by a large amount. That is this force which we are going to use, right? So just, and why this pressure force will increase? Just to keep this ratio as constant, because we have got now larger area. This is what do we really mean by hydraulic machines. This thing will be used in hydraulic lifts, like for example as to lifting any car or any large amount of weight over here, right? Similarly, this will be used in some of the hydraulic brakes as well. Now in this hydraulic brake, again we have got a master cylinder over here. In this master cylinder you have got a small piston. So to push that small piston, that's relatively very easy. And inside that we have got a brake fluid. So this blue fluid is actually known as brake fluid, which again it is transmitted throughout throughout these pipes, and it is going through to the wheels of your car, or of your any vehicle. Then after that, when this piston is being pushed, again the pressure is transmitted throughout the liquid, and again this will be actually now this piston will be actually compressed in these directions with a larger force, and we can actually stop our vehicle. So that's how the hydraulic machines actually work. So we have just drawn four pistons over here, two on the front wheel, two on the rear wheel, and then again also we have got another wheels as well, right? So that's how the hydraulic machines works. After that, now we are going to talk about pressure gauges. Pressure gauges are basically pressure measuring devices. Pressure measuring devices, what do we mean by that? Whenever you are going to measure a pressure, let's suppose you want to actually measure a pressure of, we have got a fluid over here, and we have got something, we have got an arrangement over here that we are calling it as a device which will measure pressure at this particular point. Let's just suppose we are going to talk about different devices, but as of now, let's just suppose that this is some pressure measuring device. Let me draw it clearly. Let's suppose that at this particular point we have got a pressure measuring device, right? Now what will this actually measure? So we know that mathematically we can write that pressure at this particular point, let's say this point is P, or let's say this point is A. Pressure at this particular point A, and to not, I don't want you to get confused with atmosphere, so let me use some another variable. Let's use as X. So pressure at point X is definitely, we know that pressure at point X is P naught, because atmosphere is definitely applying pressure over here, plus it is rho GH. This is what the formula for pressure is going to be. Now Px is actually known as absolute pressure. This is the correct value of pressure, because we know that atmosphere is also applying the pressure, and because of this fluid, the height of this fluid has, let's say it is h, because of that also we have got a pressure. But if you are going to talk about, if I just want to know what is the pressure difference between these 2 points, between this point and this point, so that would be just be because of this height, that is actually, that will be Px minus P naught, isn't it? Let's not talk about atmospheric pressure. Let's say we are not discussing atmospheric pressure. Let's discuss only what's the pressure difference between these 2 points. So that will be just rho GH, and this type of a reading is actually known as gauge reading. So gauge is nothing but you might have seen like some meters in circular shape that show pressures, right? So I'll make one. It would look something like this. So you have got a 0 reading over here. It can have different scales. Let's right now, let's say we are measuring it in pascals only. You can also talk about in bar or in atmospheric pressure. Like we know that 1 atmospheric pressure is actually equals to 1.01 into 10 to the power 5 pascals. It's a large amount of pressure, isn't it? So we can also consider like 2 atm, 3 atm pressure. So this is something that a gauge device looks like. Over here we have got like 0, and one particular side we have got positive reading. So if you are like going if the pressure is increasing more than the atmospheric pressure, it will be read as positive. If it is actually less than the atmospheric pressure, then it will be read as negative. So you have got different readings over here. Buffalo is obviously something like this, right? Now after this, moving on to the next topic, we have discussed what the pressure gauges is. Gauge pressure is positive for pressures above atmospheric pressure, negative for pressures below atmospheric pressure. Pressure gauges are also referred to as pressure meters or vacuum gauges, right? After this, we have got certain devices through which we can actually measure pressure. That's what I was saying, that we are going to talk about it. For example, the first one is manometer. A manometer is used to measure the pressure of a gas inside a container. So this is the definition. Now for this one, let's suppose that we have got gas over here. We have got gas filled in this path, right? This is the for the first part of the diagram, we have got both an open end over here. So this is also open end, this is also open end. So over here we have got atmospheric pressure P naught, over here we have got atmospheric pressure P naught. So that's why these two are at equal levels, are exactly at equals level. But now what happens is, let's suppose we have connected a gas supply over here. So here we have got gas. Now this gas is actually applying a pressure in this direction, that we are calling it as gas pressure. Because of that, what will happen, what we now want to do is, we want to actually have, let's say we want that whatever the pressure at point A is, at C also it should be same, because again this is what the Pascal's law said, right? it will transmit equally to that particular level. So it should be same. Now what will happen? The thing that will happen is now some of the fluid will actually ascend into the tube, and this will be actually rho gh, and this will ascend up till it is equal to the pressure of point A, right? So the access pressure that we are going to actually talk about is pressure at point C will be actually equals to P naught, that is atmospheric pressure, plus rho gh. So if you want to know the gauge pressure, so it would be Pc minus P naught, that is rho gh. Now how we are going to actually do this thing is that you will actually find out what the height is, just multiply it and you can find out what pressure you are getting, right? That's what the manometer actually it is for, right? Moving on, after that, then we have got like mercury barometer. For mercury barometer, what we actually do is we use a device something like this. Let's suppose we have got a container, and in this container, let's suppose that we have got a certain fluid, and we have dipped a long narrow tube something like this. Now what will happen? And also we have done one more thing, that we have actually there's no air over here, right? So it's so long that at this particular point we have got atmospheric pressure, but what we are going to say is that these surfaces are exposed more to the atmospheric pressure than this one, right? So we are just assuming that there is no air inside it, no air. This is very important, right? There is no air. Now what will happen? We know that we have got a fluid inside this. Now the fluid will actually try to ascend the barometer, and the reason is that this will ascend only because of one reason, that the pressure between these points, let's say this is point X, and let's say this is point Y. Now we know that Px is actually P naught, that is atmospheric pressure, but we are saying that we don't have any air over here. So to say that Px must be equals to Py, the liquid must ascend up to a certain height so that these two can become equal, and now we can also write this thing as rho gh. So a mercury barometer has a height of around 760 millimeter, and we usually call sometimes our atmospheric pressure as 760 millimeter of Hg. That is mercury actually rises up to this amount of height, and that's why we actually don't use substances like water, because mercury is actually quite dense, so it can be used but not water, right? So this is what a mercury barometer is. Now after this, let's solve some of the questions regarding these concepts. So we have got the first question, as this one is from 2024 paper of February March series. The diagram shows a rectangular metal block with the dimensions of 2.5 centimeter, 2.5 into 3 into 4.5. The block is resting in the ground. The block exerts a pressure of, so they have given us what the pressure is. What is the weight? We know again that pressure is nothing but, right now it's going to be weight divided by area, and this is actually 0.23. So weight is going to be 0.23, which is in SI unit, times the area. So area of this thing is going to be, now that's what we need to actually find out. So this is the area that we are talking about, which is in contact with the surface. So area is going to be 4.5 times 2.5, and we have got centimeter square, so we need to actually convert it into meter. So we are going to write W equals to 0.23 times 4.5 times 2.5, and times, we know that 1 centimeter is 10 to the power minus 2, so this is going to be 10 to the power minus 4 meters square. So this is going to be the correct answer. Let's quickly find it out. 0.23 times 4.5 times 2.5, and this is about this is nearly about, let's check it once again. I think we have done. By the way, pressure is also in centimeter square only. Pressure is also in centimeter square, so we don't have to actually multiply because this is also in centimeter square. So just let's just write it in centimeter square, because when we are writing 0.23 Newton, this is also in centimeter square, so this thing can be cancelled out. So by the way, this answer is going to be around 2.58, which is nearly 2.6 Newton. That's all. Hopefully you have got it. Moving on to the next one. The diagram shows a column of liquid. The pressure due to the liquid at the bottom of the liquid is 6000 Newton per meter square. What is the density of the liquid? Now, whenever we talk about questions like this, we always say that at the bottom surface, the pressure is rho gh. We don't actually add the atmospheric pressure, right? Although if they have given in the options that add like it is actually, the option says 310 plus atmospheric pressure, then obviously you are going to select that. But other than that, we are going to quickly say that rho gh is actually equals to 6000. Everything is in SI unit, so density will be actually equals to 6000 divided by g is, we are going to take it as 9.8 times depth is 50 centimeter. I will have to convert it into meters, so I'll multiply 100 over here, right? After this, let's just quickly find this one out. This one is actually 60,000 divided by 5 and divided by 9.8. That is around, that is actually it is 1224, which again can be written as 1200, which is this is what we are going to use, because we have got like the nearest option is option B. Moving on to the next one, hopefully you can see it. When a diver swims down from the surface of the water to a depth of 10 meter, the pressure experienced increases from 100,000 to 200,000 Newton per meter square. Which statement explains the increase in pressure? Now we know that why there is an increase in pressure. The density of the water increases with depth. Well, this is not true, because density is pretty much constant. The gravitational field strength also, it is pretty much constant. It's not going to decrease or increase with this amount of height or depth. The weight of the water above the diver increases with depth. This is absolutely correct, because as you're going to go down, there's more and more amount of fluid that is above you. Water cannot be compressed. Well, this is absolutely correct, but this doesn't explain why there's an increase in pressure, right? Moving on. The water in a swimming pool exerts a pressure at the bottom of the pool. Which graph shows the relationship between pressure exerted by the water and the depth of the pool? So as you are going to actually increase the depth, the pressure is going to increase, right? That's for sure. And the relation is actually directly proportional. So this is actually quite easy again, because pressure is actually equals to rho gh, where h is the depth. You can call it as d also. So pressure directly depends on the depth. A solid cube has sides 0.50 long, 0.50 meter long, and mass of 120 kg. It stands on the ground on one face. Which pressure does cube exert on the? So now this is actually quite easy. So pressure would be actually equals to 120 times g times area. When they are talking about area, it's going to be 0.50 times 0.50. So this is going to be around, so it's around 470, which will be rounded to 4700 kg per meter cube. This is going to be the correct answer. Moving on. Question 6 says the graph shows how the pressure due to liquid varies with the depth beneath the liquid surface. The gravitational field strength is 9.8 Newton per kg. What is the density of the liquid? Now, see what they are trying to say. They have said, they have given us the graph. By the way, this was the question, this was the graph that they were asking us in the previous question. They have said that we have got a graph, pressure due to a liquid varies with the depth, something like this. They are asking about the density. So let's just find the most convenient point. And the most convenient point looks, I think, somewhere over here, if I'm not wrong. Well, it's a little hard for us to see it, but what we can do is just I think this will be the point. Let's figure it out. Although it's not absolutely correct, it's a little less than 0.30, but still, if we want to find out the density, we know that rho gh is actually equals to pressure, and pressure, let's say it is 2000. So rho is going to be equals to 2000 divided by 9.8 times height is that they have given us 0.30, and I think it is a little less than that, right? So let's first find it out. 2000 divided by 9.8 divided by 0.30, so it's around, it's 680. So if I'm going to actually decrease 0.30 by a bit, it the number might increase, and that might increase up to like 820. So the correct answer would be 820 kilogram per meter cube. We can again check this one. What we can actually do is, this point seems to be at the middle of this thing, right? The height is actually 0.60, so 9.8 times 0.60. All right, I'll write it somewhere over here. For the second point, let's consider it as the height is 0.60, so 9.8 times 0.60, and this is nothing but this is actually this is going to be 5000. So if we'll find this answer, again it's coming near 820 only. This one is giving us 850, right? So the correct answer is going to be 820 kilogram per meter cube. Moving on, the diagram shows a rectangular block, same types of question. So this is the thing that we are going to come across similar types of question. Again, in this one they have given us what the force is. It is 16 Newton. And again, if you're going to find out the area of this block, this dimension is 5, this dimension is 4, so this is going to be just 20, and I think this is in centimeter square. So times, actually they are talking about just in centimeters, so we don't have to worry about it, right? So that's what the answer is going to be. It's going to be 0.80. That's it, option C. Moving on, a pressure gauge is lowered into the sea. Measurements of the pressure and depth are taken as the pressure is lowered. Which statement describes how and why the pressure changes as gauge is lowered? Density of the sea water decreases so that the pressure increases. Wrong. Density remains constant. The depth of the gauge below the surface of the sea increases, so the pressure increases. Well, yes, depth increases, and that's why the pressure increases. Height of the gauge above the seabed, that has got to do nothing. It's option B is absolutely correct. Moving on, question 9 says a manometer containing water is used to measure the pressure of a gas. All right, the density of the water is 1000 kilogram per meter cube. What is the pressure of the gas supply? So the pressure of the gas supply will be actually equals to the difference between these 2 points. So this point has exactly equals to pressure to this point, right? That's what the gas pressure is. So this difference is going to be rho gh. So rho is 1000 times g is 9.8 times, and I think what we are going to say is that yes, let's move 1000 times 9.8 times this height is actually 30 centimeter. So this is going to be your answer. Let's find it out. 1000 times 9.8 times 30. Hopefully we have done everything correct. This is in, by the way, this is in centimeter. So we'll have to actually keep that thing in also mind. This is in centimeter, so we will divide by 100. So now this will, and if I'll take this as 10, so that will be 30 into 100, that is 3000. So 3000 plus there is also atmospheric pressure. So the absolute pressure of gas is going to be 3000 pascals plus atmospheric pressure. So 3000 pascals above the atmospheric pressure would be the correct answer. Moving on. The diagram containing the sea water, the density of the fluid is 1020 kilogram per meter cube. What is the pressure at point P relative to the atmosphere? So for point P, we are going to just do one thing. We are going to find out what this height is. And that's going to be about 8. That height is going to be just 8 minus 0.6. Is that correct? Right? So this is going to be actually 7.4 meters. So the pressure is going to be rho G, let me take it as 10 and times 7.4. So now this is going to be 1020 times 10 times 7.4. That's around 75,000 above the atmospheric pressure. So 75,000 above the atmospheric pressure is going to be the correct answer. So you can see that from this small chapter, usually really simple questions comes. You only have to understand about the concept of gauge pressure, a little bit about barometer and manometer, right? Hopefully everything is clear from this small topic. If you have any doubt, if you have any query, please write down that in the comment section. We'll get back to you. I'm going to come up with another video. Till then, take care. Thanks so much. Bye bye.